The U.S. is expected to nearly double its electrical consumption from 2009 to 2017. Demand for power continues to rise while commercially viable fossil fuels continue to dwindle. Fossil fuels provide over 70% of the electrical power in the United States, as seen here, natural gas, petroleum, and coal. While cheap, even so-called clean coal and natural gas pollute our air. They're also in finite supply. Nuclear power provides over 19% of U.S. electricity. But as seen in Japan, it's not without its risks. Even without a disaster, spent fuel rods must be buried deep underground for hundreds of years. Renewable sources like hydroelectric fulfill less than 10% of U.S. electrical demand. What the world needs is a safe, cheap, and clean way to generate electricity without rapidly depleting our natural resources. It was this challenge that led to the discovery and creation of pressco. The following video is an edited version of a 3-hour independent inspection and validation by quantum physicist David Van Koevering of their final machine, pressco 2.0.
I had a lot of studies about lasers and the energy of light, the energy of amplified, coherent light. I also had a lot of experience with building musical instruments that had incoherent light, like walls, like devices that generate sound by changing the frequency of either a power supply or chopping the light into pieces of light, the aggregate, the photons of light can be chopped up. And if you chop it up, and the frequency you create a spinning device. So we built instruments that did that. I ended up with laser optical memory retrieval. And the world took off.
The best way to probably start this is when I was 16 years old, I was ahead of the curve. I was living in Valdez, Alaska, and I was working in my physics class, and the professor was talking, and I was looking across the way at the Valdez oil terminal, which they have these giant tankers that come in, and they have this ballast water that they store in the same tanks where they store the oil. They pump all of that seawater into these settling tanks, and then they try and separate the oil from the water.
Tankers arrive in Valdez full of seawater to keep them stable at sea. But this water is contaminated when it is stored in the same place where the crude oil is stored on the tankers.
Because there's no chemical way you can extract the energy out of water without having to actually apply energy, because the hydrogen and the oxygen are bonded by sharing an electron. So if you have to insert an extra electron in order to break those bonds, that's energy. And that requires energy, which means you have to put energy into the system.
Here we see the atomic structure of an H2O water molecule. Each water molecule contains 10 electrons, 10 protons, and 8 neutrons. As you can see here, the two hydrogen molecules are bound to the oxygen molecule by sharing a common electron. Comparing the electron density in octane, the primary ingredient in gasoline, water, and nitrogen, the primary ingredient in the atmosphere, shows that gasoline actually has the lowest electron density of the three. The electron density is calculated by taking Avogadro's number times moles times electrons per mole divided by 2.16 e to the 23rd, which is the number of electrons per kilowatt hour. That gives you the number of kilowatt hours per unit of measure, in this case, US gallons. All of this means that the water in their ballast tanks actually contained 90% more molecular energy than the gasoline the crude was destined to make. In addition, compressed nitrogen from the atmosphere contained almost 45% more electrons than the ballast water. As seen on the left, the nuclear energy far exceeds the chemical energy. So much so, the chemical energy must be plotted at 1/10 the nuclear energy to even appear on the chart. But while the chemical energy in gasoline is easily extracted by burning it in an oxygen-rich environment, water and nitrogen cannot be so easily burned. The challenge we faced was how to break the electron bonds within the water molecules in order to put them to work as electricity. The Large Hadron Supercollider in Switzerland accelerates protons to nearly the speed of light along a 17-mile underground tunnel. As the particles collide, massive amounts of energy are ejected, but the energy required to achieve this result far exceeds the energy output. But nature already has a way to create electricity directly from water molecules. This prompted a simple idea: replicate the natural process in a controlled environment, create lightning in a bottle. If you begin with ice at standard atmospheric pressure, it would look like the stable tetrahedral lattice structure. As the water heats up, the hydrogen bonds between the neighboring molecules begins to break. The molecules move out of their stable configuration as the crystals melt and the hydrogen bonds are torn. The solid ice transforms into a liquid. Keep heating it, and that liquid becomes a gas.
So, I came up with this theory that the logic that I came up with was an iron ball. What if I take an iron ball and I trap water, this contaminated water, inside this imaginary iron ball? And how do I need to give it as much energy as possible to try and send it through the states. It's because all I have to do is just keep pumping energy into it, and it's going to keep changing its states. And at this point, I can change the state of a matter inside of a contained system.
The idea of the pressco reactor is to trap a small sphere of water inside a sealed, nickel-plated steel chamber. The entire reactor is sealed and electrically insulated. It is then heated to 705 degrees, which also causes the pressure to rise. In a confined space, the water molecules can behave quite differently. If ice was first placed into the machine, the molecules would still be in a stable tetrahedral lattice, and as they are heated, they still phase into water. Whereas at standard atmospheric pressure, they would be preparing to phase into steam, they are unable to expand enough to do so within the reactor. So their orbits continue to expand and the molecules are packed closer and closer together. Eventually, they are packed so closely together that they no longer have any more room to expand. As each electron orbit crosses the path of its neighbor, the similarly charged electrons begin colliding with each other. The now freed electrons collect around the outside of the electrically insulated steel container and are carried away to be put to work as electricity.
Built the machine, and I'll walk you over and tell you why we designed it the way we did. We changed several times for doing all this stuff.
Boy, am I in the right place at the right time.
So I built the machine, and all of a sudden we start discovering the power came on instantaneously. We didn't have to get super fluid. We started creating power. And at first it was, 1.5 volts with, 6 milliamps, We were like, well, there's power there. We're creating it, but let's see what's going on here. And at the time we were trying to use the system itself as both, we had an anode and a cathode system so that we could loop it back around where we utilize the feedback loop it and utilize the water, the superfluidic water that we were creating as a electrolyte, thinking that we would just feed it, all we have to do is catch it in the round, and we could just feed it right back to the system feedback loop. But the problem was we had to electrically insulate the anode from the cathode while running at 3,200 psi and 751 degrees. But we were getting steam leaks at first because we were cracking the seals because we were trying to use ceramics and we tried to use epoxies, but you start entering that realm, nothing stays stable. Nothing stays stable because the temperatures and the pressures are just so massive. It's 1.44 million pounds of pressure being exerted on all directions in that thing. And we discovered we were generating power right out the gate between the anode and cathode, right off the bat. But then we started realizing that it was actually applying to other theories. It was a thermoelectric battery that we were really creating. going in. So it worked, but it was low voltage, low power. It really wasn't what was happening. So I ended up getting over here, and I'm moving wires around one day, and Jason is falling asleep because he's just bored out of his mind because I'm sitting there going, I don't know what's wrong. And I'm trying to figure all this out. And all of a sudden, I just pick up the voltage meter and plug it, stick it in the freaking ground on the wall, and I stick it to the thing, and it melts the end of the tip of the hole of my voltage probe. And right as the meter just goes, spikes all the way to the top, and then it's toast. It doesn't read.
You were needing a ground.
Well, I needed earth ground. And the moment I did that, I closed the circuit and I went, God, I was reading the whole thing. I was looking at this the whole wrong way. Instead of trying to close loop the system, I worked the ground. And the whole purpose, that little switch right over there was set that if it ever got out of control, I could dump to ground.
Yeah.
But what I didn't realize is that I could have been running to ground the entire time. And pulling my electricity. So turn the machine way back, backed it off on pressure, backed it off on temperature, and the next thing I know, I had a steady like 38 volts.
That was first.
And the moment that I had that, I was like, well, it's 38 volts. There's nothing over there, and the meter's reading it. I pick up my little analog meter, and the analog meter's freaking out. It's not really knowing what kind of power it's getting, but it's saying it's somewhere around 38 volts, which was far more than I could have possibly been creating by leaking electricity from anything else in the system. So at that moment, I woke him up, and I'm like, we got power. And he's like,
How long did it take to make the phone call?
he just kind of opens his eyes and is like, what? I was like, come here, look. And so I put the probe on, and I'm like, look, the computer was wrong, the sensors were hooked up incorrectly. I was completely had this thing wired wrong. I was looking for it in the wrong place. The power was zero the whole time. Ran the system and started noticing that I wasn't getting decent power. I was expecting this nice little plane out and this nice little spread of electricity, and I was like, when I sat down in our first meeting, I'm like, we can generate power, all we have to do is create the right electronics, and I can just flatten out that, I can just drop it down to right where I want, I'll invert the power, and we can run AC all day long. But when I started doing it, all of a sudden I started seeing blip, 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 I was seeing all these oscillations. So I started counting the variance of where these things were, the frequencies, the amplitude of these things. I started noticing that the frequency, the measurements on it, and granted I'm using very raw tools, but I started noticing that the frequency of the voltage pulses was exactly correlated to hydrogen and oxygen, the right amount of proportions of hydrogen and oxygen molecules, which meant that I was in fact doing something different to the two different molecules as I was destroying them, essentially. I was peeling off all of their electrons and turning it into electricity that I was essentially liquefying, if you will, to turn it into
All of that is
so
theoretical stuff needs to look at the best tools he can get.
trying to think of ways that I could turn that into a usable power. But discovered that there's no electronics out there that are off the shelf that can handle that kind of juice. Because I've already got this electricity. I'm not trying to run it from a generator. I can't modulate my wave in any way. I've got to take it and electronically modulate it because I am directly converting matter into electricity. There is no intermediate state. I don't have all these machines spinning. There's nothing overcomplicated. It's theoretically as efficient as it can possibly be. I'm taking, I have a 6-inch diameter sphere inside that chamber. That contains enough power for 3.2 megawatts hours worth of juice out of that tiny bit of water. And that's enough to power up everything. Yeah. That's enough. That's a massive amount of power for that. The energy density of that is just phenomenal. We started working on the ionic propulsion drives and started working on ways of actually taking electricity, converting it into ions, creating ionic wind, and actually utilizing that as a form of propulsion.
Which is a vacuum, next generation spaceship.
So, and that's what they're actually utilizing. Some of the stuff that I was working on back then is actually now powering several of the satellites. They're using it for control systems. They can't actually use it for primary propulsion. Energy density is still the issue. They can't create enough power. Well, this would solve that issue. Is that I was trying to come up with a way. All I have to do is come up with a power generation system, and I can create all the ionic wind I want and send us to any interstellar body I want at the speed of light, because I can own no object can theoretically exceed, Newtonian physics. You can't exceed the speed of your exhaust, but if the speed of my exhaust is the speed of light, nothing restricts me.
He's right.
So,
Mark that one down, he's fast.
so I can't stop. I can't be stopped.
You have the best demonstrated evidence that I have heard about. I haven't seen it, but that I've heard about. Potential pushing past threshold. Because you're doing what no one else has claimed yet. And I'm listening. You said something that was an error so far. I didn't know. Right on. The most fascinating thing is that he trusts his feelings. You don't want somebody telling him what's right. You want somebody to give you the tools to do it. He knows it's right. You can't trust him. If I was going to write a check for $1 million, for $10 million, I could. That's good as the word get up. Yeah, I'll say that on camera. Whoever you are, if you could write that $10 million check, he's earned it. If I was going to write that check, I'd put it here. No, because you're out there far enough, and you're not doing foolish things. And if you find one, I think you've got enough integrity to say, whoops, that won't work. Because you've already said several times to me, I didn't write them, that I could be beaten. You found some things about the anode, the cathode that you didn't need, and you took it out. The inventor that can't back up is wild. Because he doesn't know when he's wrong. If you don't know when you're wrong, you're a money thing.
Yeah.
What if we talk about the toys that we've bought so far?
Okay, yeah. Well, I'm thrilled to be here, guys. Okay, show me the hardware.
Okay. So I want to show you. I want to show you this first.
Let me insert a little comment here.
How are we
We're doing good. We're doing good. I'd like to kind of make some logic points here,
Okay.
and give a sense of history of what's happened. Jason,
Oh yeah.
we were originally working with Jason prior to even knowing Apple on this premise that we are now developing. Jason is a mechanical engineer, has a lot of experience in that side of things. Jason has some theories about creation of energy, and he at one point came to Eric and myself and said, I know this guy, Alan. Okay. What you're about to see is the result of their efforts over this last 7 or 8 months.
So, before I get to that, this was the original device. This is my iron ball. Right? Built this 3 inches of solid aluminum and all the
Don't ever destroy it.
Yeah.
Send it to the Smithsonian.
Oh, yeah.
Bob Hogan and I got stuff at the Smithsonian that we thought was junk. Okay?
So we originally tried it with this thing. You had a concept of aluminum lighter. It would be very corrosion resistant, so it would build up a nice little layer of aluminum oxide to protect it from destroying itself. It would still conduct electricity. It would, oh yeah, camera. So we thought about, we were going to put this all together. We had the anode coming out the bottom, and we actually built this little reflector on the bottom. You see that little hollowed out spot there?
Yeah.
The idea would be that would capture all the electricity. And at one point, I came up with the idea that I wanted to have a little mirror shining at it, so I thought that would be the best description if we're taking solar energy and converting that radiation into thermal and then converting it into electricity. So I thought that would be a good demonstration. Jason's like, yeah, I ain't waiting for a sunny day and 9 hours for the sucker to heat up on a sunny day.
We're going to build a furnace.
So then why don't we just use a propane burner? And I was like, all right, that'll work. So we put the burner underneath here. We found that, just the heat.
Were you guys involved at that stage?
Oh yeah. We've been involved prior to Alan's.
Okay.
We discovered that the problem was that he was so intense that it would start causing deformities. The lid wouldn't seal, and actually I've got drawings of how this is actually assembled because it's not just a flat lid. There's actually a flange that slides down inside there to create the seal.
The main pressco reactor is shown here with a flange-shaped lid bolted securely in place.
We knew that it would this was actually engineered to 200,000 psi, so it theoretically could have held it to far above what we needed to, at least the thickness of the aluminum. The problem was bolts were popping, the practice of putting it back together and all those things every time became just a bear. And we eventually decided we could not work with this anymore, it was swelling so much, so we came to the steel. Why don't you go ahead and kill the heat, because it's going to be went to this design, which without having to re-engineer everything, we needed something that was electrically grounded. So we discovered that Portland cement, when it's completely dry, doesn't conduct any electricity. So we built these little insulators so that they're actually welded to that frame, and the machine in the center is hung on those 4 bolts so that it's not touching ground anywhere. And that bolt right there runs out of my main power line. So we were trying to keep this thing entirely electrically insulated was a real struggle. But what we tried at one point, we were trying to run this electrical band heater, so that's what the heater is around it. The idea being that we could take the energy we were creating, it was already electrical, we could convert that back into resistance energy and have the thing close loop itself. But once we discovered we were creating more power than even that band heater needed, and we needed to create the thermal energy, we could loop the whole system, make it run all day long, all on its own. The problem was that by having it plugged into the wall at this stage, we ended up running a Tesla coil around the whole thing. So we ended up electrifying things, and we're ending up with like 800 volts because it ends up pumping in all that stuff as a coil and essentially a glorified transformer, essentially converting that electricity. So it really was running it through it, and it really wasn't showing what we needed to show. So
I appreciate he could say that. Because if he couldn't say that, he could have misinterpreted that information. And some might not have known.
I was really happy at first until I realized, crap, that's not even real.
But the fact that he say that, to me, to verify, it's the integrity of the person not trying to pull the wool over somebody. He can say it. That means he's going to say it again. If he finds another one, he's going to do the same thing.
So it's essentially a 400-pound block of steel. It is my iron ball. And we nickel plated the inside of it. So we actually got the plating and we nickel plated it, which
removes some porosity.
It removes the porosity as well as protects the iron, because the nickel is it creates that nickel oxide, which seals it off from corroding our steel and constantly eating it, a little bit of it away. Because running at these kinds of temperatures, these kinds of pressures, we're essentially forcing that water as deep as it can possibly go into that steel. So the more we can pull that back, the better.
You're stopping rust.
So we built this thing, and instead of trying to bolt the whole thing together, we just flat out welded it closed. Realizing that we didn't need to get inside there anymore. We could extract samples throughout our pores at the top. There's little valves. You see the 4 little holes on the top? Those are burst seals, so that they'll blow up. So the energy goes straight up if they have to. And I have carbon dioxide in here that I can ventilate up there as my cooling system, my fire suppression system. So what I did is that little tube that comes out of the top. I can't measuring. There's no sensor on this earth that I have discovered, and I haven't been through every single catalog and talked to hundreds of people that can read water at that kind of temperature and that kind of pressure. It just doesn't exist. You can read them either way. You cannot read them both. So we discovered that we may have to build some we discovered that even that about the anode.
Those could be other patents too. Because you're building an industry.
We talked about that.
You want to control those kinds of tools.
We talked about that with even like what we learned about the ceramics and things like that we discovered we could build similar. When we start telling people what they need, they're like, you're going to have to invent it, basically. Okay. So what I did as a solution was that I can measure a gas at that pressure. So by running this tube all the way through, as that water expands, the water expands, pushes back, and pushes on the air trapped inside here, and pushes it to read my meter. So that I have this panel is separated from the unit itself, which is the way why it's put with these little paint gray blocks. So that's what these meters are reading. These are meeting the pressure up of it. And then I have a thermocouple that's put into a thermal well, and that's down inside there, which is coming out of that wire and then reading into my little fidget right here, the first little fidget, which is glued to the outside. I have my little meter right here, which is telling me, it's still 129 degrees inside there.
Yeah.
That whole thing in there. So it's hot. So I'll take you back here so you can see inside of the cooling bed. So this was the cooling system that we had. We're running down through these wires, running down to this, and then go through that, and run through cooling back through this. And I even have the fluid coming out here for all the wires to cool. So there's my little silly green, connected via USB, and there's my voltage and amperage sensors, and they're connected up to a diode so that I get feedback. And I had to just take as much power as I
So
could.
the electronics are pure.
So, but it's all running parallel because I can't run it in serial because I just can't handle that amount of juice. So I'm trying to run everything in
And the
parallel.
batteries
The
are,
batteries are connected to an inverter outside. Originally, I intended on running the juice through the battery, thinking I would be able to control it. So the batteries simply are backup power for the computers. They don't do anything else. They're connected
did you have a
directly.
battery overload at that time?
What's that?
Did you ever have a battery overload?
I didn't even try it. I tried it. I picked up the cable and I was gonna try and connect it, and before I did, I hooked it up to a meter, and it was just, I actually bumped it against the thing, and I had a wrench in my hand, and it fused the wrench to my hand. It literally just, it hit white hot within an instant. I knew it was way more power than I could handle. So we put this little box in here, which this was my little transformer I had hooked up to the hall sensor. It's actually hooked up a little different right now. So I'm using my high voltage probe resting on my wire, and this is connected to the little voltage sensor inside there. And then my amp meter was running across through this thing, so it's just picking up the magnetic frequency.
Okay, for the sake of documentation, if an inventor is covering something and a guy like me shows up, you won't open the boxes, because if he's got something hooked up wrong that's showing a false result, he's going to hide it.
Yeah.
There's no hiding here. Everything is open. Everything appears to be correct.
But you can see the oscillations that it's got. They're very, very strange. It's not at all like a DC. It's not like an AC power, because it's not a nice even little curve. It's
You got more than the machine is capable of measuring.
and the
It's
sensitivity of it.
confusing.
So that's my thermocouple inside there. That's the top one. The coolant is actually what the temperature is inside this. Oh, no, that coolant one is actually up there. So that's reading the temperature up top. So it's 108 degrees up there. You got my pressure right here. It's 284. This is 289. So they're within a tiny percentage point of each other. You can see my Gauss meter.
Yeah.
It's just bouncing off the charts. It doesn't even really know what to think of it. So this is the data from all the different sensors. My current temperature, or my temperature, pressure, current voltage.
And
my
this
Gauss
this
meter.
software you developed personally? Or
Yeah, I wrote all the software. I wrote all the software for
Would you
the
write it
sensor.
in what?
It's all written. This is all written in NI script. So you can notice this is your X value. This is your time. So you'll notice that all of them are a tiny bit. It can't read all the sensors at the same time because this tool can't read them in parallel. It's
What's
just
the
not.
frequency of this computer? What's running?
It's got quad core 2.6 gigahertz. I mean, it's pretty decent. But the sensors themselves don't have that kind of resolution. So these are the values. So if you can tell right here at this point when we were running this unit, it was at, temperature was 750 degrees. It was running 3,200 PSI. And I was generating 71 watts, or 71 amps of current at 946 volts, gave me 67,402 watts.
Wow. Wow. Subject to some massive error someplace, you got something powerful happening here.
Well, considering the burns that I had for a while
You
on
know
my
that
hands,
it's
and
valid, it's not just
Yeah.
on a screen.
yeah, I mean, we've seen the sparks fly. We've melted lots of things, so we know no matter what, whether it's
You build a
50,000.
very expensive welding machine, if nothing else. Any other questions you have for me?
What? I'm curious. What do you think? I mean,
Well, I've been
it's-
trying to say I trust.
Well, I guess.
My trust level is as high as it could be. I think your integrity is enough. I've heard you say no several times. You're not going to hear that from me.
Pressco received an enthusiastic endorsement from Vancouvering. Numerous additional tests and demonstrations continued to validate the results. Future tests showed that as the reactor cooled, its positive charge resulted in a reverse process by drawing in additional electrons from the Earth's ground. This meant that two machines operating on opposite cycles could exchange electrons indefinitely with the only loss of energy due to electrical resistance. We believe that pressco is the first machine to demonstrate a safe, reliable, and cost-effective way to directly generate electrical power from thermal energy. This project was made possible by Alan McGann, Chief Innovation Officer and Lead Engineer, Jason Sawyer, Chief Technology Officer and Mechanical Engineer, Lynn Kiesecker, Chief Operating Officer and President, and Eric DeYoung, Chief Executive Officer and Chairman.